Thanks for watching AI Weekly Update from Henry AI Labs. This week we'll cover a lot of interesting things like a new Imagenet classification, state of the art, and a lot of interesting articles and tutorials around model distillation and self-supervised learning. We'll also look at a really interesting write-up from Jeff Dean on the deep learning revolution and the advances in hardware and the future of chip design. Thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos. This AI Weekly Update will begin by looking at the new Imagenet classification, state of the art, presented by Google AI with a novel approach to model distillation. Then we'll look further at model distillation with this great article and code tutorial from Floyd Hub, distilling knowledge from neural networks to build smaller and faster models, particularly in the context of natural language processing for model distillation. Then we'll look at this great write-up from Jeff Dean, the deep learning revolution and its implications for computer architecture and chip design, discussing some of the history of the slowing of Moore's law, AI and compute, and discussing a lot of interesting directions for the future of chip design and deep learning and machine learning. Then from Google's AI blog, we'll look at a discussion about MobileNet v3 and the MobileNet optimized for deployment on the edge TPU, and a discussion about hardware-aware neural architecture search for the sake of faster inference on these mobile devices. This weekly update will also cover this great blog post from Lillian Wang on self-supervised representation learning, going through a lot of the different self-supervised learning tasks that have been designed for images, videos, and reinforcement learning. Then we'll look at this great article on accelerating random forests by up to 45 times using CUML, a discussion on how the random forest algorithm is embarrassingly parallel and how it can easily be distributed across different cores of the GPUs and accelerated by using the rapid CUML library. Then from Facebook, we'll look at new progress in using AI to detect harmful content, things like the self-supervised XLM model in order to make use of English to improve detection in foreign languages as well. Then from Stanford, we'll look at controlling assistive robots with learn latent actions. This is the idea of having these low-dimensional codes that can be used to control the high-dimensional degrees of freedom of the assistive robotic arms. Then we'll look at the use of convolutional and recurrent neural networks to do epilepsy prediction from this EEG signal data. Then from Google, we'll look at this new approach to self-supervised learning for pitch estimation and then its application to separating different audio signals from audio files. Then we'll look at this paper, Specializing Word Embeddings for Parsing by Information Bottleneck, which won the Best Paper Award at the EMNLP conference. Then from Nvidia, we'll look at this company, Harrison.ai, and their success in predicting in vitro fertilization and different applications in medical imaging. Also from Nvidia, we'll look at Facebook's Fashion++ model and a new video further explaining the algorithm. Then we'll also look at a discussion on mixed precision computing from Nvidia, and we'll look at this new Kowlin library that is facilitating 3D deep learning research, a PyTorch library that makes it easier to upload these different kinds of things like voxels, point clouds, or these meshes to do 3D deep learning and 3D computer vision. Then from the batch, we'll look at all these different articles that they've presented and a note on doing machine learning with small data. One of the most interesting updates to AI this week is a new state-of-the-art on Imagenet classification at 87.4% top 1 accuracy, denoting a 1% improvement over the previous state-of-the-art. This technique uses something called knowledge or model distillation. The idea here is that you have a teacher network that is usually a really high, large capacity model, such as an Imagenet B7 or any of these kinds of massive models, and you use this in order to smoothen out the labels on the dataset and make it easier to distill the knowledge or train a student network. Usually this is done with a smaller capacity student network, and it's frequently associated with speeding up inference, reducing memory costs, and these kinds of things. So the idea is basically, if you say you have the CFAR10 dataset, where you have 1 denoting, say, cat and then 0 everywhere else, you would run the Imagenet B7 or some kind of higher capacity model to predict the label distribution on that image, and rather than having 1 for cat and then 0 everywhere else, you'd get this distribution, which is called a soft distribution, where you have, say, 0.95 for cat, and then 0.04 for dog, and then, say, for something like ship or truck, you might have like 0.00001. And so doing this kind of label smoothing essentially helps the student network get a better sense of the data distribution, and it's better than any kind of prior you could enforce on the label smoothing. So in this paper, Self-Training with Noisy Student Improves Imagenet Classification, instead of having the teacher-student network be higher capacity than the student network, they actually are going to have larger and larger models where the teacher has lower capacity than the student up until the end where they have the same capacity. So another interesting thing about this is that they're using a different pipeline. So rather than have the teacher network just run its predictions on the original data set, they're also going to use this large unlabeled 300 million JFT data set. So they're going to have the original Imagenet data set that the teacher network is trained on, and then it's going to run its predictions to pseudo-label the unlabeled data set. So this is really similar to the semi-weekly supervised training framework from Facebook, where they're doing a similar kind of pipeline, but they're relabeling the 3.5 billion images that were previously weekly labeled by using the hashtags as people upload the photos to Instagram. So a lot of other interesting things in this paper is the use of noise, things like having dropout, stochastic depth, and data augmentation to improve the model, and then exactly the pipeline, the algorithm for how they do this. Also interestingly is this kind of robustness for free that comes up with it, shown in this table. And then I think another really interesting detail to this paper is the scaling up of the efficient net family. So basically they go from a series of efficient net models, so they go from B1, B2, B3 when they're doing the teacher to student. And I think that this is a really significant part of this pipeline. And you'll see a lot of these other papers that say things like in the distilled BERT where there's some kind of correlation between the family architectures. So it's definitely a really interesting paper and definitely something worth checking out. If you're furtherly interested in my take on this paper, please check out the video I posted on the Henry AI Labs YouTube channel, Self-Training with Noisy Student, 87.4% Imagenet Top 1 accuracy, getting a little more into the details of this paper. Floyd Hub has published a really great tutorial describing model distillation and then having a code example for doing the distilling BERT into a bi-LSTM model. In this article, distilling knowledge from neural networks to build smaller and faster models. So the article begins with a description of distillation and a description of how you have these original labels that have then been smoothed by using the teacher network. So for example, in the task of predicting the next word, you might have a sentence like the quick brown fox jumps over, and then you would mask out this word and have the language model predict the masked out word. So you can see already how having one-hot labels over these masked out words doesn't make a lot of sense compared to having these soft label distributions that the teacher produces for the student network. So a good example of this in the jumps example is that you can have all these different words that precede jump. Jump over, jump to, jump the, or jump 42 for jump 42 times, just showing that natural language is very unpredictable and it's really hard to have these kind of one-hot labels for learning this kind of next word task. So in the article, they then detail this pipeline. You have the pre-trained teacher model, then you fine-tune it with the training set, and then you use this to have the new label distribution that you use to train the student. Although the student has this kind of alpha and the 1 minus alpha, I think it's supposed to be ordered, parameters to weight the hard labels or the 1000 kind of label compared with the soft labels produced by the teacher. So also in the article, they discuss this kind of idea of having a family of architectures. In the Hugging Face implementation of this in Distill BERT, they use a smaller transformer model. So it's not the same as a bi-LSTM. A transformer model is basically the idea of BERT. It's just a smaller version of kind of the BERT architecture. So in these paragraphs, the author describes how this kind of family of architectures is important for model distillation. Then the article discusses using data augmentation in this pipeline and how you can use the pre-trained language model to construct new sentences in ways that make sense compared to, say, just randomly swapping out nouns for nouns because you might corrupt the label of the sentence. The article then goes on to discuss the idea of using temperature in this framework. So the idea of temperature is that usually you have this kind of softmax distribution that you use in order to have the labels kind of sum up to 1, and you can add this temperature, which is included in the original paper by Jeff Hinton, Oriol Vinyals, and Jeff Dean, about how you add this temperature term to the top and the bottom of the softmax function in order to kind of smoothen out this distribution and make sure it's not too biased and is, informative enough. So then the article goes into the code, showing you how to use these things like the fast text word vectors and all these different kinds of things if you are interested in doing this yourself. And then in the kind of conclusion of the study, the author discusses having a 65 times less computation to run inference on a single sentence with the final model, and then 57 times later in the terms of the trainable parameters. And then also in an ablation study, the author finds that the use of data augmentation is enormous for the success of this model, as well as many other things related to the experiment, things like how many augmented examples are produced and different lessons learned that the author learned through doing this example. So it's definitely a really interesting article, one of the best descriptions of model knowledge distillation in the context of NLP, and definitely a great thing if you're interested in getting started with this for yourself. The deep learning revolution and its implications for computer architecture and chip design is a really great write-up from Jeff Dean following his keynote at the 2020 International Solid State Circuits Conference. This article discusses a lot of interesting things about machine learning and then the computational devices that run machine learning. So it starts off with a discussion about the advances in machine learning, things like the advance in Imagenet classification accuracy. You see the trend towards solving Imagenet, which is really interesting. And then the article goes on to talk about these interesting trends like the slowing of Moore's law, the computation done by OpenAI in their article Compute and AI, I think is the title of it, where they showed the doubling time in computational demand every 3.4 months of some major contributions in AI. And then also, interestingly, the growing rate of more people publishing papers in machine learning and these kinds of areas. So this graph shows the slowing of the Moore's law. This graph shows from the OpenAI's AI and compute the increase in compute used for a lot of the recent models like neural machine translation, neural architecture search, and AlphaGo 0. and then some graph about the new machine learning papers that are being published. So the article then goes on to have this interesting discussion about trying to deploy these kind of speech recognition models require just scaling up the data center like crazy. So they look into specialized hardware, inspiring the design of the TPU version 1, which is the single chip designed to target inference acceleration. They discuss the use of lower precision weights using 8-bit integers in the TPU version 1, and then some of the different performance gains, 15 to 30 times faster than the GPU or CPU at the time, and then having more efficiency with computations for power usage. So then the article goes on to discuss different chip companies like Cerebras, Graphcore, and Nirvana, different exciting things that are being developed for this kind of hardware specialized deep learning like inference and training, discussing the differences, the challenge between designing training chips compared to inference chips, with designing training chips being a little more challenging. Then it goes into a more specific article on low precision numeric formats and kind of the idea of reducing precision for inference acceleration. And then also interestingly is this discussion of how there needs to be kind of like, since chip design projects take about 18 to 24 months to finish the design and then bring them into a data center environment, you need to have this kind of co-design where you have people who are kind of forecasting the future trends in machine learning to kind of see what kind of design of the chips will be best. And particularly in this article discussing the future potential of these kinds of mixture of experts models and the need to have this kind of co-design with the mixture of experts networks, although it's definitely interesting to think about all the different ways that this could play out and the different kinds of futures for the chip designs to accommodate the future of these neural network architectures. So then the article goes on to using machine learning for chip design, having cases like where you use reinforcement learning to play the game of placement and routing, similar to like how DeepMind did the data center control, where you use this kind of machine learning algorithm in order to solve these NP-hard optimization problems. So also in the article, it goes on to discuss like data structures and how you could do these learned index structures and how this compares to things like B trees, hash tables, and these different kinds of data structures. So it's definitely a really interesting article, also discussing the mixture of experts model, which is this model that is kind of sparsely activated. So you have this big neural network, and then when a task comes in, the model knows how to route it through the big neural network to produce different outputs and more efficient, higher performance, but definitely a really interesting model that I think has a lot of potential. Obviously, Jeff Dean thinks it has a lot of potential. And then it's really interesting just to think about this kind of an architecture. So this is a really great article discussing a lot of interesting things relating computing and then trends in machine learning and deep learning. So also after reading this paper, The Deep Learning Revolution and its implications for computer architecture and chip design, you might want to familiarize yourself with this mixture of experts model and read the paper, Outrageously Large Neural Networks, the Sparsely Gated Mixture of Experts Layer. And you might also be interested in this article on Int4 precision, the discussion around using lower precision for inference. In this case, Nvidia's experiment with using this to set the record in the MLPerf inference benchmarks. So definitely a lot of interesting things around reduced precision inference and kind of quantization and these kinds of ideas. From Google's AI blog is a discussion on the latest installment of the MobileNets, the MobileNet version 3, and then the MobileNet optimized for the edge TPU computing, which is installed in the Pixel 4 with the Pixel Neural Core, containing an instantiation of the edge TPU architecture. So MobileNet version 3 is the latest installment in the MobileNet family. The original MobileNet introducing the depth-wise separable convolution for faster and more efficient computer vision models like Imagenet classification and COCO object detection. Then MobileNet v2 had the inverted residuals and linear bottlenecks, adding this kind of structure to the feature maps in order to make the networks more efficient. Then the MNASNet paper basically brought in this kind of reinforcement learning neural architecture search into the MobileNet family and had this kind of search space described here in the paper to search for the MobileNets. And then also interestingly is the paper SqueezeNet, which has this kind of design for feature maps, the squeeze and expand where you kind of compress the feature maps and then expand them and have this kind of architecture for these faster, more efficient computer vision networks. So in MobileNet version 3, they combine the ideas of neural architecture search, a lot of the recent state-of-the-arts, in order to design the next generation of MobileNets with better performance. So some of this performance is the MobileNet version 3 large, 32% more accurate on Imagenet classification, while having 20% faster inference compared to the previous MobileNet v2. So also really interestingly to this blog post from Google's AI is the importance of having the kind of hardware-aware neural architecture search. So in the plots in the bottom of the article, they show how the MobileNet Edge TPU, when they are doing the neural architecture search, optimizing MobileNet v3 for deployment on the Edge TPU devices, it's able to achieve this higher accuracy with faster inference times. But then when they switch the same model into the CPUs, the original MobileNet v3 performs better. Even the MobileNet v2 performs better than the optimized for the edge version. So it's definitely interesting to see this kind of hardware-aware neural architecture search for the sake of having faster models that require less memory as well. From the Rapids AI blog is a blog post on accelerating random forests by up to 45 times using the CUML libraries, and a miscellaneous discussion on different cases of building random forests and then speeding them up by using the Nvidia Rapids library and putting it on the GPUs with these CUDA data frames and the CUML library. So the article begins by discussing random forests, kind of having this idea of having different decision trees trained on different subsets of the data, and then kind of these optimizations like having different ways of splitting the features and accelerating how quick you find the feature to split on for each node. So say you're at this decision tree, you'd first look at this feature, is the size greater than, and then some attribute, and then you traverse the decision tree in this way until you reach these leaf nodes to make predictions. So in the article, they discuss different cases on how the CUML library is helping to accelerate this building different forests across multiple GPUs. So one of the interesting things is building individual decision trees in this kind of random forest ensemble kind of framework is an example of an embarrassingly parallel algorithm where you can easily just distribute it, give it different sets of data, and then build it on different cores. So in this case, they present an example of how similar the CUML random forest API is to, say, the sklearn version of building a random forest, and they discuss using Dask to accelerate this if you're training this on multiple GPUs. So the Dask data frames is a little different from the CUDA data frames for distributing the these kinds of tabular data set workflows across different GPUs instead of just having, say, a single GPU. So then in the article is the benchmarks compared to sklearn and CUML. So these bar charts, the height of them shows the speed up in different cases. So say that you are building 100 trees, each with 8 as the depth, the maximum depth, you would get about a 30 times speed up in this case. So in this case, in this article, the results presented kind of show this interesting trend where they're having you can't, as you increase the depth of the maximum depth of the random forest, each decision tree, you get less of a speed up, which is interesting. And in the article discusses about how this will be improved in the future. Also, interestingly, in the article is this kind of greater than linear scaling up due to the way that the data is partitioned across multiple GPUs. So this is definitely a great article, really interesting discussion of rapids and the speedups on building random forests. And you can also check out this notebook from the Rapids AI notebook if you're interested in trying this yourself. Lillian Wang posted a really great article on self-supervised representation learning, which surveys a lot of different self-supervised learning tasks to help you to get a sense of this kind of learning algorithm. So from a high-level idea, self-supervised learning is this idea where you have a bunch of unlabeled data, and then you can construct some kind of task such that you can have a supervised learning algorithm from unlabeled data. So a common example of this is the case of masking out words, where you have a massive set of text, and then you mask out words such that you can now do supervised learning to predict the masked out word. So some cases of this are having this exemplar CNN where you construct different classes by doing data augmentation, and then you kind of treat each of these as their own class. So now you're doing supervised learning on the unlabeled data set by using data augmentation to form these kinds of auxiliary classes. Another case of this is using rotation, where you take images and then you randomly rotate them such that you have this new auxiliary class and you can do supervised learning. So there's other cases of this, like doing having the patches where you predict the relative location of the patches to each other, and this is another case where you can construct a supervised learning task from unlabeled image data. So also interestingly in this article is discussions of different cases that kind of have self-supervised learning go wrong, like chromatic aberration, where you can just kind of rely on the way that the colors in the image are rendered in order to do tasks like the relative patch location, and other details like this in robotic learning, how the model can exploit the pretext task, the self-supervised learning task, in order to kind of solve it without really learning like a useful or generalizable representation of the data. So another case of this is counting features that discusses the math of this. Colorization, where you mask out the RGB and then you predict the grayscale. Another interesting case is where you say just take the R and the G, or the red and the green channels, and then you predict kind of the blue channel from those channels, which is also a pretty interesting colorization task. So other examples of this are generative modeling, cases like say you crop out this patch and then you fill in the missing patch and use this to learn representations, or cases like where you have the bidirectional GAN, such as the big BiGAN from DeepMind, where you have sort of the features and you have the encoder that takes the original data set and encodes it into the vectors, and then you might use these vectors on the original data as features for some kind of new classification model or something like that. So also in the article, it discusses a lot of interesting video-based self-supervised learning algorithms, things like tracking moving objects, where you have kind of predicting the motion of the objects, and then things like frame sequence, where you kind of predict the order of the frames. A lot of these tasks, it makes a lot of sense how you would construct these self-supervised tasks from unlabeled video data like frame sequence and predicting which frame comes after which frame. Things like video colorization, similar to the images, but kind of in this case adding this idea of having a reference frame for the colors, so kind of adding more structure compared to the image case. And the article goes on to discuss a lot of different things about self-supervised learning in robotic learning and kind of reinforcement learning and these different kinds of tasks. So this is definitely a really, really interesting article, great for getting a sense of the different self-supervised learning algorithms that are useful and are being used. Specializing word embeddings for parsing by Information Bottleneck won the Best Paper Award at the EMNLP conference with a really interesting approach to compress word vectors by having this kind of variational autoencoder and making it so you say take a high dimensional word vector and then compress it into a low dimensional representation, and then on the decoding end it's judged based on how useful it is for doing this task of dependency parsing, which you can learn more about by going to the Stanford NLP group and reading up about dependency parsers and constructing these kinds of graphs that relate words to each other. So it's definitely a really interesting paper. I didn't quite have too much time to get into it, but it looks like a very interesting technique for reducing the dimensionality of word vectors. PyTorch has published a really interesting video discussing how PyTorch is being used to power autonomous vehicles at Caltech. So particularly the video goes through this neural lander case, where on the baseline you're not really able to model the dynamics of the drone to land it when it gets closer to the ground. But by approximating it with the neural network, they're able to achieve this kind of landing without just kind of like turning it off and just dropping it from a certain height. So it's a really interesting article and video, and then there's also an article that you can check out as well, linked in the video, that discusses about the use of PyTorch in order to approximate these kinds of dynamics for autonomous vehicles. Another interesting update to deep learning and AI this week is the use of convolutional and recurrent neural networks to achieve this 99.6% accuracy on seizure prediction in these EEG kind of electrical activity in the brain kind of devices to extract this kind of data and then use it to train these models that can predict seizures. From Stanford's AI lab is controlling assistive robotics with learned latent actions. So to give a high-level overview of this study, they have these kinds of robotic arms to facilitate tasks like taking this Tupperware out of the refrigerator, and the interface requires kind of switching between modes frequently in order to control all the different degrees of freedom on this robotic arm in order to manipulate it and do these kinds of tasks. So in this study, they're looking to have a more low-dimensional interface that can translate to the high-dimensional ways of that the robot arm can move, because it has all these different degrees of freedom, different ways that it could possibly move. So they describe in this paper, their algorithm for doing this, how they're trying to train these low-dimensional latent spaces that can be used as the interface to control these kinds of assistive robotics. From Facebook's AI research blog is new progress in using AI to detect harmful content. So some of the ideas in this blog post are things like using self-supervised learning like the XLM learning framework in order to do this kind of multilingual, sort of to have this kind of detect hate speech in different languages, and how you can have things like more English data or more English text data is able to improve the performance of the model in other languages as well through the use of this XLM self-supervised learning framework. So also in the article, it discusses this more holistic approach to understanding the different ways of different content that they want to flag. You see that they're grouping it all together into one model that has all the different kinds of labels onto it, compared to having separate models to classify each kind of offense, like nudity or violence, these kinds of things. So they discuss improvements on things like detecting selling drugs on Facebook, and sort of the increase in how good their systems are getting at improving this kind of detection, and particularly the contributions enabled by self-supervised learning like XLM. Another case of the success of self-supervised learning is in Google's AI blog SPICE, Self-Supervised Pitch Estimation. So in this case, they take the unlabeled data and then they automatically shift the pitch in different models, and then they have this encoder that encodes the new sample and then sort of has this loss to make sure that it can identify how much the pitch was shifted. So in this article, they show how doing this kind of self-supervised learning algorithm is able to increase the benchmark on separating different audio files or different speakers from the same audio, I think. So this plot shows the differences between the SPICE algorithm, which is self-supervised, compared to the CREPE, which is a fully supervised model, and so showing that the SPICE is able to outperform it in most cases on this task. Nvidia has open sourced a 3D deep learning research library named Kowlin in PyTorch. So interestingly, they discussed the idea of preparing a 3D model has been reduced from 300 lines of code down to just 5 with the introduction of this open source library. So 3D datasets and 3D applications are useful for things like 3D object recognition, 3D segmentation, like taking this character and then segmenting the different body parts, useful for things like animation, for rig a character for animation, or to customize the model to generate variations of the object. Things like taking a two-dimensional image and then producing a three-dimensional image, things like GANs or different ideas for doing this, and then different other applications of three-dimensional deep learning. So you can check out the library on GitHub, NVIDIA GameWorks/Kowlin. I can see some of the different applications of it. And then also you can, if you want to learn more about it, you can check out their research paper, Kowlin, a PyTorch library for accelerating 3D deep learning research. From Nvidia is a discussion on the idea of mixed precision computing. So in this article, they're relating the the numeric precision used for the pi, the 3.14, 1.59 number, and then kind of relating this to illustrate this idea of different levels of precision, and then also then coming back to how mixed precision is used to train deep neural networks. So first they show this example of how you could represent pi at double precision, single precision, and then half precision, and sort of showing the kind of what this looks like where you have less bits used to represent the different numbers. So they discuss how mixed precision is where you might have two 16-bit matrices multiplied together and then having the answer be 32 bits. So this is kind of the idea of mixed precision and kind of moving from different precisions for having like 32-bit and 16-bit floating points when training these models. So they discuss how they get this 3 times faster when they are benchmarking these kinds of mixed precision systems. And they discuss a lot of different use cases for things like earthquake simulations and then detecting weather patterns and all these different cases of where mixed precision is accelerating the training of deep neural networks. So you can also check out this this tutorial on automatic mixed precision for deep learning. You can check out how you might use this in TensorFlow with this kind of code, and then how you might use this in PyTorch and also Imagenet. From Nvidia is a description of Facebook's Fashion++ system that uses GANs in order to separate texture and shape and then suggest different suggestions for outfits. So it's kind of like a digital assistant, and definitely interesting is this video that describes it in better detail. You can see how the Fashion++ system is suggesting these kinds of minor changes to outfits in order to improve fashionability. And you can check out more about this research by checking out the paper, Fashion++, Minimal Edits for Outfit Improvement. NVIDIA's AI blog discusses some of the interesting achievements by Harrison.ai to improve in vitro fertilization with computer vision. So some of the most interesting things about this study, other than the increase in accuracy up to 93% accuracy, where the article previously cites that this kind of prediction is usually under 50%, depending on different cases. So I thought something that was really interesting about this blog post is that they don't just use single frames to predict the embryo development. Rather, they're actually using these video models to have this kind of temporal modeling in their models, which I thought was really interesting. So you can watch this video to learn more about Harrison.ai. Definitely another really interesting company about improving this kind of medical imaging and these different kinds of applications. They also discuss kind of doing this chest X-ray detection as well, and kind of all these different applications of deep learning and computer vision. This week's edition of The Batch from DeepLearning.ai begins with a note from Andrew Ng about why machine learning projects fail, particularly the case of small data. So examples of this are, say you have 1 million labeled images and you want to detect scratch phones in a smartphone manufacturer, and you wouldn't have that many examples of actual scratch phones. So you might need to get good performance from a machine learning model, computer vision classifier, with 100 or even 10 images for this application. So this problem is also something that appears a lot in X-ray diagnosis, medical image applications. So discussing things like this kind of distribution, where you have this really small number of samples, and you can't solve this problem with things like just giving higher weight to these misclassified examples. So some of the solutions to these small data problems are transfer learning, one or few shot learning, and then encoding priors into the system with the designers of the algorithm, and then data augmentation and data synthesis. So definitely a really interesting discussion on small data and how to improve systems to achieve performance on these kinds of data sets. The batch then continues to discuss the case of when Uber's self-driving cars killed a pedestrian. So in the analysis of this system, they detect how it wasn't really able to use temporal information. It was switching between detecting the pedestrian as a bicycle or a car, and then kind of just overall discussing what happened and sort of steps forward into how to make the deployment of self-driving cars safer and better tested before they're put on the roads. The batch goes on to discuss deep learning being used to detect fraudulent trades on the Nasdaq Stock Exchange. Then it discusses a new algorithm for looking at how we fine-tune word vectors. So when you take the new data set that you're fine-tuning the word vectors on, kind of keeping this consistent with the original word vectors in the more general word corpus. So then the batch goes on to discuss neuroevolution and different algorithms, such as the POET algorithm that is using neuroevolution to evolve the environment, and then the reinforcement learning controlling agent that is used to control this bipedal walker in this case, and then also the use of neuroevolution in the case of DeepMind's AlphaStar, the StarCraft 2 player. So neuroevolution is definitely a really interesting use of randomized search, and definitely different from direct gradient descent and these kinds of ideas, and a really interesting algorithm for the development of future advances in neural architectures. The batch then goes on to discuss how computer vision is being used to count fish, and in order to kind of detect their age by detecting how long the fish is, which is a good proxy for their age, and then how it's being used in order to control these fish populations. The batch concludes with the discussion of the Facebook OctConv model. So it's a really interesting architecture that achieves faster inference and better performance by separating these convolutional filters into low frequency, where you have just kind of like the outline of the penguins, compared to high frequency, where you have things like the details of the image. So it's also interestingly, the Fashion++ system kind of does a similar thing of separating out the shape, which is more low frequency, and then the texture, which is more high frequency. So it's definitely an interesting innovation in the direction of faster, more efficient convolutional networks that have faster inference by explicitly separating out low and high frequency convolutional filters. Thanks for watching this edition of AI Weekly Update from Henry AI Labs. Please subscribe for more deep learning and AI videos.